Hi everyone, welcome back to IB Math. Hope you're doing well. And today we begin chapter 24, last chapter in your book of new material. Um, I want to talk today about the normal distribution, and I got a lot of stuff to show you here. If you want to follow along in your book, there's a lot of things I don't want you to have to write down everything. So if you want to print this out from the notes section in eCampus, or if you want to follow along with your textbook, that's fine too. And I'm going to kind of highlight some of the things along the way because there's a lot of good information in your book here. But I do want to kind of go through here and point stuff out as I go through your book, and I don't want you to have to write every single little detail down. So I'll kind of talk us through some things that we're talking about today. Before we get to normal distribution itself, I want to go in and talk about what we've been discussing with probability and mean values and standard deviation and things like that. So here's just an example. There's this breeder who's catching fish. We have a mean weight and we have a standard deviation of that weight. And then we do a histogram and we see that it's kind of a bell-shaped curve, right? And that makes sense because standard deviation is the distance from the mean, and most of the values are going to fall within that mean, that average, pretty close. And we're going to have some values, some bigger, much smaller, much bigger fish way on the extremes, right? But not many of them. So that's great. But what if we want to look at certain parts of that? What if we want to look at the percentage or proportion of fish who are say between 4 and 6 grams? So somewhere in the middle here, like between 4 and 6, like just those fish. Or what if we're looking for, as it says here, can we find the weight of which 90% weigh less than? So maybe here's the 90% mark, and 90% of them are here. So what percentage is that going to be? And that's what we're going to talk about in this chapter here when we start talking about the normal distribution. Chapter 24 that we've just started is all about this in different applications that you can have for it as well. So if you remember last chapter, we talked about discrete random variables, right? So we talked about the probability of x occurring, and x was always a non-negative integer, right? So when we looked at probabilities that x could be less than 2 or greater than 3, but we looked at integer values when x was 0, 1, 2, 3, 4, etc., all the way up. A little bit different here. We're going to talk now about continuous random variables, which are a little bit different because this can take any real value, right? We were looking at when x equals 1 or x equals 2, but what if I could have situations where x equals 4.69? That's not going to happen when I'm rolling dice, right? I can't roll a 2.396, but in other things, decimals could be values here. So at that point, what I want to look at is not just individual x values, like a particular value of c or a particular value of d, but I'm going to look at all these real number possibilities in here as well. And what that's going to do is that's going to now become an area under the curve. And where did we do area under a curve before? Yes, that's right. We did it in calculus last semester. Particularly in quarter 2, we started looking at integral values, and integrals represented areas under a curve. So this curve, what we're going to do is the formula for this curve is going to be our probability density function, and we're going to use that to find particular ranges of areas here. So if you'll notice, obviously, a couple of things, because if we looked at the whole area under the curve, so remember how integrals work, just kind of a recap. The integral from a to b is going to be the area under the curve from, let's say, a was here and b was here. If this was my entire curve, and we know that all the probabilities together have to equal 1, right? So the area under the curve is going to equal to 1. What we're going to look at is the integral from c to d, right? And we're going to look at that area under the curve, or the integral value of that. And that's going to be our probability that x lies somewhere in that interval. It could be any real number in there. Couple of minor details to go through when we're talking about these continuous random variables is that the probability that x is exactly equal to something is going to be 0. And the reason for that is, and here's a good example, if you try to, like, let's say you weigh an egg, what's the probability that's going to weigh exactly 72.9 grams? Well, the probability is 0. Even if you had a scale and you happen to get an egg that read on the scale 72.9, what that scale really means is that it's somewhere between 72.85 and 72.95, right? It's just where the scale is accurate. Even if we had a scale that was accurate down to the nuclear level, where we're measuring the weight of atoms and things, you can never get an exact weight of an egg. So the probability is going to be zero of an exact value. So we're always going to be looking for a range whenever we talk about continuous random variables here. And so that means, and since it can never be equal to, we're talking about equal, all of these probabilities basically mean the same thing. Where it says, X is between C and D, inclusive or not inclusive, or both inclusive or one inclusive, it doesn't make a difference either way. Those are all equal to the same. So that's just something to mention there. Okay. So now let's talk about what we call a normal distribution. Normal distribution is when we have a bunch of data and that it all went, when we look at the set of data, we look at the mean, we look at the standard deviation, we have data tends to distribute itself normally or approximately normally. And what that means is when we're looking at physical attributes of a population or score tests or things like that, we can calculate the mean, the standard deviation, and if we were to look at a histogram or a graph of this, we would see a couple of people scoring much higher, a couple of people scoring much lower, but a lot of people tending to score right around the mean. And this happens all the time. And how do we get this, or why does this happen? Well, of course, not everyone is going to get the same test score. Here's an example about oranges, and oranges tend to vary, right, because of genetics or the sunlight or weather conditions. But the large majority of fruit are going to have weights very close to the mean, right? And there's going to be a few that are much heavier, much lighter, and that's where we get our standard deviation, and we're going to get a bell-curved graph for all of this, kind of like we've seen before, and I just kind of mentioned it up there with the fish example. So here is our normal probability density function. And I'm not going to bog us too down on this exact formula of what it's for. Really not something we need to know right now, because it's a standard formula for the normal probability density function. But a couple of things that I do want you to look at is that with a normal probability curve, we do have an asymptote. And as x approaches positive or negative infinity, the asymptote is the x-axis. So it's getting really close to, but never hitting zero in these extreme cases. And as a result, that means the area under this entire curve has to equal 1, right, from negative to positive infinity, because all the probabilities together have to equal 1. Of course, the large majority of those numbers are found where? Really close to the mean, because that's how a normal distribution works, right? Most values are going to be close to the mean. You'll have some values that are outliers way far away from the mean, but the large majority are going to be pretty close to the mean. How close and how many? That's what we're going to talk about with a normal distribution. So I want to kind of just briefly go over some of the math behind this, and I want to show you how this works. So if this is our formula, right, for the normal distribution, do you remember in calculus we took the first derivative, which was the slope, and we took the second derivative, right? So the first derivative was the change of the slope, right? And then we looked at the second derivative, which was the instantaneous change of the slope, or where the slope went from increasing or to decreasing or vice versa. And we had inflection points in our graph, right? So if you look at this graph down here, and I'm going to come back to this, but here we have a graph that is concave up, right, and then concave down, and then concave up again. That's when we have these points of inflection. So those points of inflection occur where the second derivative equals 0, if you remember that from calculus. So what happens is, if I take the formula that we have up here for f of x, that is, we established up here, right, is going to be our probability density function, and we take the first derivative and then the second derivative, and then we set the second derivative equal to 0, which we do right here. Then if you solve for the second derivative equals 0, you're going to get this, and this is what I want to draw your attention to, that x is equal to the mean plus or minus the standard deviation. So what it says is this points of inflection of my graph occur when I am one standard deviation away from the mean. So whatever the standard deviation is, if I go left or right of that standard of the mean, that's going to be where my points of inflection are. And so it says that for the normal curve, the standard deviation is uniquely determined as the horizontal distance from the line of symmetry, which is the mean, to a point of inflection. And that is always what happens on a normal distribution curve. So, and then because of that, here are some percentages that are always true for every normal distribution curve. Regardless of the data, if it's an exactly normal distribution curve, this is where you're going to find your probabilities. So if I look at all the different values over a set of data that are normally distributed, you're going to find that 34.13 and 34.13, or approximately 68.2%, are within one standard deviation of the mean, meaning 68% of the values of the data collected are going to be within plus or minus the standard deviation away from the mean. And that makes sense, right? That high number, 68% of the values are within standard deviation away from the mean, or the overall average of all the values. And then if we actually look at two standard deviations away, so all of this under here, all of this is going to end up being 95%. And that's where our standard deviation comes into play as far as helping us to make this curve. And then if you look 3 standard deviations away, which is all the way to here and all the way to here, you're going to get 99% of your data found. Now, does that change? Do these percentages change? No. But does the curve change based on your mean and your standard deviation? Well, definitely. So for instance, if you have a curve that looks like, let's say you have a very small standard deviation. Let me go back up here to this example up here. If I have a very small standard deviation, then my normal curve might look like this, right? Where this is my point of inflection, this is my point of inflection. Now that mean, and here's my mean, right? That means I have a very small standard deviation, but I'm still going to get, this is going to be that 68% of the values in between there, and then 99%, et cetera, all the way down. So based on the curve is going to be slightly different shapes based on what the mean and what the standard deviation are for a particular set of values. Let's look at an example. So this says the chest measurements of 18-year-old male footballers are normally distributed. That means we have a good normal distribution. It has a mean of 95 and a standard deviation of 8. So could we graph this? Well, sure. So if I graph this down here, notice my mean is 95 and my standard deviation is 8. So if I go 8 below 95 and another 8 below 95, if I go 8 above 95 and another 8 above 95, I'm going to get those x values. And those are all standard deviation distances away from my mean. So the first question is, what is the percentage of the footballers with a chest measurement between, ridiculous example, chest measurements, of footballers, 87 and 103. What's that standard deviation, or what is the percentage of footballers? Well, 87 and 103, that is right here. That's this distance, and it's going to be the distance between one standard deviation. Well, we already figured that out. We know that that's going to be, as it says here, 68.3%. And what about those between 103 and 111? Well, that's going to be, let's look at, erase this, 103 to 111. That's going to be this distance right here, which we already knew was going to be 13%. And then we could talk about some other ones. What's the probability that a footballer chosen randomly has a chest between 87 and 111? Well, let's look at 87 and 111. So 87 and 111 is all of this percentages right here. So it's 68 plus 13.5 and is going to be this calculation right here, 68 and 13.5, so 81.9%, or a probability of 0.819. And it says find the value of K such that approximately 16% of the chest measurements are below are below K. Well, where would that be? Well, 16% below, we know that's this part of the curve right here. And what is that going to be? Well, that's going to be 95 minus 8, so it's going to be 87. So only 16% of the footballers are going to have a a chest measurement below or less than 87 centimeters. And that's the type of thing you can do with your standard deviation and your mean and your normal distribution curve. So just to get started, we have a few exercises I want you to check out in section 24, numbers 1, 3, 4, and 10. And these are all about using, just like we did in that example, using the normal distribution curve given a mean and a standard deviation to draw the curve and then figure out exactly where the percentages of the distribution lie. And it's always going to be the same. As long as you have a mean and a standard deviation, these percentages here will always be the same for a normal distribution curve. So that's it. So again, don't forget, if you have any questions, please feel free to ask on the message boards or send me an email. And please don't forget to upload your assignment into eCampus. Take care. We'll talk to you next time.